Here's problem 37.9. In a double slit experiment, the distance between the slits is 0.2 millimeters and the distance to the screen is 150 centimeters. What wavelength in nanometers is needed to have the intensity at a point 1 millimeter from the central maximum be 80% of the maximum value? We have D is equal to 0.2 millimeters, which is 2 times 10 to the minus 4 meters. We have that the distance to the screen, L, is 150 centimeters, so that's going to be 1.5 meters. We have that the distance Y to the point on the screen is 1 millimeter, so that'll be 10 to the minus 3 meters. And we want to find the wavelength. Our general equation is that the intensity at some point is equal to the maximum intensity times the cosine squared of pi dy over lambda times L. So we want to solve this for lambda. And in this case, we're told that at this particular point, it's equal to 80%, 0.8 of the maximum value. So the maximum value is canceling out. We want to solve cosine squared of everything in the parentheses for 0.8. Let's take the square root of both sides and then the inverse cosine. So we have pi dy over lambda L is equal to the inverse cosine of the square root of 0.8. And when we calculate this inverse cosine, we need to make sure that our calculator is in radians mode. Okay, let's solve this for lambda. So we are going to have that lambda is equal to pi dy over L times the inverse cosine of the square root of 0.8. So this is pi times d, 2 times 10 to the minus 4, times y, 10 to the minus 3. L is 1.5, and then we have the cosine inverse of 0.8, square root of 0.8. It was 0.4636. So what do we get? I get 9.03 times 10 to the minus 7. Meters. If I wrote that as nanometers, that would be 903 nanometers. So that is the wavelength of the light that will correspond to having a central maximum of 80% intensity at this point of 1 millimeter up on the screen. Wavelength is 903 nanometers.